Hello, my internet friends. Today is a historic day in our journey through the Ethernaut series. Reason being is I was unable to find an answer that fit the current state of this Reentrancy challenge. So, long story short, I didn't get the answer. I know what the problem is, I know what the flaw is, I know how to attack it and all that stuff, but I couldn't actually get it to work within Remix when running it against this contract. So, with that being stated, if you figured out a way to solve this challenge, please either link your answer below or put your answer directly below in the comments, because that would help soothe my need for completeness. Because if we do these Ethernaut series all the way through, we'll have 25 check marks, or 24 check marks, but 25 challenges. And that is annoying. But at the same time, share my notes here. This is a question that I asked myself, and this is kind of an analogy or an image that kind of encompassed that. I kept on asking myself the last week or so when trying to work through this challenge, am I a failure if I don't complete it, or am I going to learn no matter what, and we can continue through the other challenges as well as future content that can help me learn more. And I didn't necessarily want to have this small kind of issue with implementing the attack to halt my ability to learn new things in the future. So, with that being said, we're going to walk through the challenge. We will walk through the code, we'll walk through everything, but at the end, you will be unsatisfied without an answer. So now that we've gotten that out of the way, like I said, I'm learning. This is a compassionate Dylan that's saying that even though I failed, you're learning a lot, and that's all that matters. Cool. So I have a bunch of notes here, and before I go through the notes, we'll kind of summarize the challenge. So this challenge is called Reentrancy. Now, with Reentrancy, this is a common attack that a lot of people discuss. Reason being is that Reentrancy, historically, was a very popular type of attack, and it is still prevalent today, and there's actually a blog post I'll link you to that refers to somewhat recent attacks of how people are increasing the complexity of Reentrancy attacks that are still useful today and sometimes work against the known preventative measures, which is quite interesting. So with this attack, they're basically saying some things might help are understanding untrusted contracts and the kind of the issue with that, fallback methods, throw revert bubbling. That's interesting. I didn't really see much of that when I was researching this, but there you go. Actually, this might be a term that I would understand if I Googled, because this bubbling and throwing kind of align with the hack. All right. Sometimes best way to attack contracts with another contract. Okay, and then see help for beyond the console. So this is referring to Remix. This is referring to the fact that we have to write a contract to actually attack this contract. Fallback method is what we're going to use partially to attack this contract. And this is basically referring to this. So that, in a nutshell, is what they're asking for us to do with the tips they provided. Now, this is our contract that we're trying to attack. I've placed that both inside of Remix, so this is the contract from there, and also the attack contract we're going to walk through. But before we do that, we will walk through the attack at a high level, and then we'll talk about the code later. So like I said, this is a Reentrancy attack. Now, there's a great explanation here that I'll link in the description as always. And this is from QuantStamp, and the graphic that I'm going to talk through is what they've kind of published inside of this in this blog post. In addition to that, the challenge that we're doing today via Ethernaut is actually most likely inspired by a historical attack called the DAO attack. And that DAO attack was what actually originated the separation between Ethereum and Ethereum Classic when they had the original hard fork back in the day. And I bet if we do a hard fork, I just want to see if there's a date. So yeah, 2016 is when that happened, when they did that hard fork, and the DAO inspired that. So what is a Reentrancy attack? Well, this graphic helps explain it pretty well. So say we have our target. So this is our target here, and this is the DAO contract, and then this is our attacker contract. So this is the malicious contract. So when we deploy our target contract, we have a few different functions in here. One of which matters most is the withdraw function. Now, our contract here, they're going to initiate a withdrawal and we're going to call this withdrawal function. This withdrawal function is then going to transfer a set amount of ether that was asked to originally be withdrawn. Now, an important thing here to point out is that when it sends the ether, it's going to pass along gas here. And when it passes that along to send that to this transaction or this contract, as a malicious contract, does not have a receive function, but it does have a fallback function. Now, this fallback function can receive ether on behalf of a contract. And the important piece here is this fallback function is going to have another withdrawal function baked inside of it. So when they send this ether back to us, we're immediately going to kick off another withdrawal. And when we immediately kick off that other withdrawal function, it's going to then loop back and re-enter, hence reentrancy. That's why it's called a reentrancy attack. We're going to re-enter into the withdrawal function once again, and we're going to then withdraw that same amount. But the important thing here is that when we do that process, the update balance piece of this function isn't happening until after the transfer occurs. So that means that we're going to be able to keep on re-entering into this contract and siphoning off all the funds, not just our funds, but everybody's funds, before our balance is updated. And when we do that, that's going to give us the ability to basically re-enter the contract consistently over and over and over until we, we steal everything. And that's basically what happened with the DAO attack that's mentioned here. Now that's a high-level intuitive understanding of what's occurring here. And that's kind of one of the biggest takeaways that you'd want to take away from this challenge is understanding how this attack functions and how it works and what to avoid and how to fix it. Now, below here, I have both the flaws of this target and this contract and this attack, and also the fixes to it. Below that, I have some more information, but before we go to that, we'll start with this. So what are the flaws? Now, in the above explanation, I was talking about how the update followed the send transfer, which is up there. Now, there's this common pattern called check, effect, interact. The target address that we're attacking above and the weakness in the target that we're targeting in Ethernaut incorrectly orders that pattern. So instead, they're doing check, interact, effect. Now, interact and effect should be swapped. So effect should be second, interact should be third. Reason being is that if we do it vice versa, that allows us to continuously siphon off the funds because we're interacting with external contracts before the state is affected and our balance is set to what it should be. Now this is the wrong order, and when you see functions that are ordered this way, you automatically can assume that there might be a fault in this or some sort of ability for us to exploit this. Now another piece here is their use of call. Now I don't know if in this example they use call, they say transfer, but if I'll review the code later, like in depth, but I just wanted to specifically point out this piece here. You can see that we're doing message_sender.call. Now, you'll see in some explanations that with security inside of Solidity, it's better to use send and transfer because that limits the amount of gas that's sent out after a function occurs. So if you send out the 2300 gas after you've sent the ether, that limits the amount of gas that can be utilized in the execution of the contract you're sending this ether to. But with call, instead you're actually sending everything. Not everything, but you're sending all the remaining gas after that transaction is completed. You're not limiting it to a set amount. Now, some people say this is good to actually set the amount to 2300, but down below, I'll explain that's not necessarily the case. Reason being is that call is most likely going to be the longer term fix that you'll want to keep and not use send or transfer, but like I said, we'll explain that later. So this is a flaw here because we're using call. Another thing to point out here is there's an assumption baked into this contract, this creation of this contract via the developer. As the developer was creating the target contract we're going to attack in Ethernaut, they assumed most likely that the only party that was going to interact with this target contract was going to be an externally owned account, e.g. a human. So that's going to be, a person. But when you deploy anything out in the real world, out in the wild, everything is fair game. And when everything is fair game, that means that contracts have the potential of actually interacting with this contract you've created. And if that's the case, that means that they have the ability to execute certain types of code. And they can also utilize that code to then potentially re-enter back into your contract. that was another big thing here, was the assumption, right? Now, the next thing here, the next kind of fault or flaw is, I wouldn't say this is really a flaw, but it's I guess the method of which we're gonna utilize our attacker contract to exploit the weakness in the target contract. And that's going to be the fallback function. Now, as we've discussed in previous kind of lessons and previous challenges, the fallback function itself is the ability for a contract to receive ether as well as message data when there's no other function called. And there's, I think there's a good explanation linked here that walks you through what that is. Yeah, so this breakdown in the Stack Exchange explains the difference between receive and fallback. Here you can see basically this is saying empty call data, and this is any other function matches, blah, blah, blah. And what that means, simply put, is the receive, let's do black. The receive function you can put into your contract is capable of receiving value, so that's basically ether, and then it's unable to receive call data, which is basically data that's trying to be changed in the state of a contract. Now, a fallback is a alternative to receive. If receive is not established or kind of called out in the contract that you set up, then fallback can be called out and be utilized on behalf of receive. And with that being stated, they can receive within a fallback both call data as well as value and ether. And that's kind of what it does in a nutshell. Is basically if you've written a contract and you want to ensure that you can receive ether from other contracts, and you've not specifically established, I guess, an ABI encoded function that other contracts know what to use. So if you've created a function that says send me ether, and in that function it does a bunch of stuff, if the contract that's calling your contract, and let's draw this out. Let's just draw, right? Let's draw somewhere where there's space. All right, so simply put, is if we have contract here and a contract here, and if this contract is calling your contract to send ether, and then when they send that ether and they don't specifically call a function inside of here that's specified, so if they don't call, we'll call it, SE for send ether, a function that we've created, if they don't call that, they're going to automatically either hit the receive function if we've put it in there, or they're going to hit the fallback function because they've not specified the send ether function. Now, if we did have them specify this, these wouldn't be relevant because we would call this and it would do its stuff. Now, that's kind of the purpose of that part of the contract, because most of the times when contracts interact with your contract, they're not necessarily going to know what functions to call in the ABI encoded version of that. So that's the fallback piece. So those are the flaws. Now, on to the fixes. Now, there's a few different fixes that you'll come across when researching reentrancy, and some of these are still valid and some of these are kind of less utilized today. First things first is mutex. Now, when doing a bit of Googling around this, mutex is not anything new to Solidity. It's something that's been utilized in computer science for many, many years. And the purpose of a mutex is basically to lock or enforce access to a certain number of resources or a certain number of executions within a function to ensure that you're either not overly utilizing resources in the computer science world, or you're not necessarily executing or re-entering into a function as it goes through its entire process, which is kind of more correlated to crypto. So if we go back to the notes, there are a few posts that I wanted to share. So the Wikipedia I'll share obviously around kind of what mutexes stand for and what that means. But if we go in this blog, they've actually walked through a pretty straightforward understanding of what mutexes are and how they're utilized. So we can simply we'll kind of walk through what they've put here just so you can understand what's going on. So here you can see that we have a simplistic contract, right? Two functions. So in this function we have transfer, and then this function is a withdrawal. So I don't think they showed where this was initialized. It didn't. So you're just going to have to assume that there is a modifier or a thing that we've created that fits that lock requirement. So we have a function here and a function here, right? So we have a requirement at the very beginning to ensure that this this requirement is not locked. So we want to keep it as false. So locked means true, unlocked means false, or not locked is false. And here, after we've made that requirement, we're going to then lock it to true. We're going to execute our function as we go through here, and then we're going to unlock it to false. The reason we're doing this is because when somebody enters this function and asks for the transfer to occur, they can't necessarily come back around and re-enter until this is completely executed, because it's locked if we try to re-enter. And the reason we know that is because when we try to re-enter, the locked variable is going to be set to true, so we won't be able to continue. Once this is completed, then it transfers to false. Once it goes to false, then we can go back into the contract. But by that time, we've already changed the state, and everything should be, kosher in a way. And the same explanation is occurred here. So that blog post is pretty good. Stack Exchange is good as well. Another thing I wanted to point out here is, in addition to creating your own kind of locked variable and all that stuff, OpenZeppelin has created a ton of useful tools in contracts, and one of those is actually a modifier called Re-entrancy guard. I think it's Re-entrancy guard. Yeah, Re-entrancy guard. And in here is basically the snippet of code that explains what that is, and I can quickly walk you through that, but I'd recommend just reading this blog post to get an idea of what Re-entrancy guard does and its purpose and its need. And also they kind of give some prefaces around some of the stuff of how this isn't necessarily utilized for everything and shouldn't be utilized for everything to ensure that re-entrancy is prevented. So that's good. The code here, to quickly kind of give an example of what's going on, is we have an abstract contract here called Reentrancy guard. And then they have really great explanations if you just want to read through this and understand it yourself. But since you're watching the video, I'm assuming you want me to kind of explain it. So we have a few state variables here that are all private. So we have one state variable here that's not entered, which is 1, entered is 2, and then we have a status. So here as a constructor, when this abstract contract is deployed, we're automatically going to set the status to not entered. So that's basically saying kind of false for the locked piece. Now if we go down here, we have a modifier that we're going to leverage in our contract. So when we have our contract written over here, and we have our stuff going on, we got all our code, right? We're going to include this modifier at the end of our function that we want to utilize it for. So if we have a function here that's executing, then we're going to put this modifier here. So we ensure that this entire thing executes and is locked as it goes through. And the explanation here is basically requiring that the status is not entered. So we have to ensure that this is false. And then once we begin the execution of the contract, we'll then change that to entered, which is true, kind of referring to the blog post. And then after that, we'll continue our function. So that's kind of what this means here is once we get to this and this is set to true, then you can continue the function, which is going to be over here in our contract. And then after we get to the end of the function, we're going to change the status from entered to not entered, false, so it's unlocked, so people can then come back into this contract and start over again. And Reentrancy guard is a common modifier that many people utilize in certain circumstances, hopefully not all the time for everything. So that is that fix. The next fix is probably the most important and something that more people should utilize instead of trying to utilize transfer or send to limit the gas or to use mutexes to lock the function. And that is the pattern of how the code is laid out. And that's the check, effect, interact pattern that I referred to previously. So if I go to this link here, that doesn't want to open, so we're going to have to do it the old-fashioned way. Maybe not. Wait, no, I have to click it and then do this. Yeah, there we go. And leave that. All right, so this is just the Solidity documentation that gives you a brief explanation of what the check effect pattern is and how it's utilized. There's a lot of blog posts that you'll find written about this topic, but there's a pretty sweet image here that kind of explains what's going on, and I kind of wanted to use this because for me, images are more intuitive. All right, so here you can see that there's a big X here. It says this is wrong, don't do this pattern. And the reason being is here we're doing a check. So we're saying, okay, we want to require that the amount is less than or equal to the sender's balance. If so, then continue. If not, say invalid amount. And then the next item here is setting a variable. So that is not relevant here. And then we have our interaction piece. So interaction is saying, I want to call the value. So we're going to basically send this amount to whatever target we're sending it to. And then the last part is affecting that balance. So we're going to take that balance and we're going to knock it down to 0 after we've interacted. Now remember, I said this is the wrong order, right? Because we want to check, we want to then affect, and then we want to interact. And that's where they're saying there's a big check mark here and saying this is correct. Reason being is that we have our check right here, so we have a requirement that's doing its thing here. Then we have our effect, so we're taking the balance down to 0 after we've said that we want to send this much. And then we're going to then send the amount that we said we wanted to send. And then after you do that, then you know that when they try to re-enter into this contract, the balance has already been affected, so they're unable to actually continuously keep sending it. And that's a really important thing to understand and how that code should be structured. So always remember check, effect, interact. Check, effect, interact. Check, effect, interact. Good. Glad we did that together. And here's the last piece of how you'll see sometimes people talking through reentrancy, and they'll specifically state that the one of the good approaches is actually utilizing transfer and send instead of call, and that's to limit the gas usage like we talked about. But like I said, that's not a long-term fix and shouldn't necessarily be what you default to. And there's 2 good blog posts that kind of explain why that's the reason. So if we do send, maybe transfer. Here we go, transfer, call, send. So here you can see them talking through in this blog kind of why this isn't the fix. But in addition to that, there's actually a better post here from the diligence team talking about how you should stop using transfer, as well as I'm sure they reference send here as well. And the reason they talk through that is basically, yeah, you can see we recommend to avoid transfer and send. And this goes back to the point that I was making that in the future, the gas limit of 2300 doesn't necessarily isn't going to stick around, you know, and also the value of gas may change over time. So the amount of gas needed to execute a function what's inside of a contract might increase. So utilizing something that's limited by the gas isn't necessarily a long-term viable fix. You should instead focus on the pattern of how the code is structured instead of doing the alternative. So that's a really good explanation there. All right, so those are our fixes. Those are the flaws. So now I'm going to walk you through some quick resources. So our handy dandy Ethernaut series here for Web3 Developer Guy. You can see he posted this in December 2020 and it's 2022 now. So I'm assuming what's happened is there's been changes in Remix, or there's been changes in the challenge we're targeting for Ethernaut, and the solution he provided didn't work for me. But hey, it might work for you. So that was a good explanation to understand what reentrancy is. Another great explanation, as always, is the smart contract programmer person. So they do a really good job at explaining what reentrancy is as well. Some other solutions that I wanted to share. So this is a lengthier webinar on reentrancy, and it's kind of both protecting against reentrancy, but also kind of like a commercial, a promotion for Mirage Web3. So take that with a grain of salt. You can watch it, not watch it, it's up to you. And then this blog post here is actually quite interesting. So this I would highly recommend reading, because this is the one that I referred to previously that basically walks you through the historical attacks of reentrancy, and this is a great graphic. I love when people put like historical photos in blogs, even though it's not really connected. And they specifically talk through these examples here that are all semi-recent, right? So these are all from 2020 and 2021. So it gives you an idea of how the reentrancy attack hasn't necessarily disappeared. It's just increased in complexity. And there's a reference here of actually cross-function and reentrancy. So instead of going back to the same function, they'll go back to a separate function, which is kind of convoluted and complex, but definitely something you should check out. And with that being stated, we are going to review the code. And I put it in VS Code because it's easier for me. All right, so this is our target. So we'll start with the target. The target here we have, per usual, we have our pragma, so our compiler version. We want to change this to 8, remember, and we want to get rid of the floater, and we want to keep it solid. The import function you'll want to adjust as well. Reason being is that the target, when trying to save this, and actually you don't really need to, I don't think, in Remix you don't have to save this because you just need to use the functions in the other one. But anyways, we're importing safe math to ensure that we're not necessarily opening ourselves up to integer overflows and things like that. Here we have our contract, so it's called Re-entrance, and we have a few state variables and a mapping. So our state variable, we're basically utilizing safe math for the uint type of integer. Then we have our mapping, so this is basically saying that what is the balance of this address, so that's the mapping that we're setting up here. Our donate function is basically saying that we want to donate to an address, so that's going to be our target address we're donating to. This is public payable. and we're going to say that we want to add a certain amount of value. So the add is referring to the safe math that we've imported earlier. And then we're going to say we want to add the set amount of value to the balance of 2 that we're sending it to, and then that's going to map it to the state variable here. So once we've done this, and once we've donated, we're actually going to be a part of this mapping now. We've officially become a part of the contract by donating here. Now the next thing is balance of. So this is just a simple helper function, and this helper function is going to say, what is the balance of this contract address. So once we've donated, we can then check our balance and see how much value is in there. And you can see it just returns a balance for you. And now down here, this is where the magic happens, right? So this function here is what we're going to exploit. And let me undo that. So this function, the withdrawal function, is what we're going to take advantage of. Now, with the withdrawal function, it's going to take an amount. So how much do we want to withdraw? Here, we're doing our check. So this is remember our check effect. So let's remember this, our check effect interact. That's the way it should be, right? So here we have our check, and this check is basically saying, I want to ensure that the sender that's withdrawing has a balance that's greater than the amount they're asking for. So you don't want to only donate 1 Ether and ask for 100. That's not going to pass here. So that's the check first. Next, it's going to say, okay, if this is true, then I want to take that amount that they've asked, and I want to send it off to the sender that requested it, and I'm going to send all the remaining gas so they can make their execution. And then if this is true, then continue. If it's false, then don't continue. Now this if here, I wasn't really 100% sure what this was doing, which may be partly due to the reason why I wasn't able to pass this challenge, or maybe not. My assumption is that it's kind of rehashing the same stuff here. So it's basically saying if the result's true, then amount. Then provide the amount back. I don't know. But anyways, this here is our interact, right? So remember, we've just crossed our hairs. We put interact second instead of third. And then the last thing here is our effect. We're going to decrement the amount that we requested from the balance of the person that requested it. So you can see this is off, right? We're doing check interact effect instead of check effect interact. That's the issue. Now we're going to take advantage of that. And quickly we have a receive here. So this is basically stating that if anybody sends Ether to this contract without specifically calling donate, then that's going to fall into the receive, and they're going to take it on. Cool. So that is how this functions, and then this is our attack contract. So per usual, this is our compiler version. We are importing this contract here, and remember it's called Reentrancy.sol. Actually, no, that's wrong. This should be, it's because I copied and pasted this from Remix when I was tinkering with it. So if this was going to be in here, this would be called ETH10, but it would be correctly spelled. Groovy. So it would be something like that, where you're basically importing that contract in here so you can then access those functions that you want to call and interact with. So we have our contract called attack, and in here we're establishing a state variable for target. So we're going to basically bring in the contract from the target contract and put this into the target variable. We have a constructor. So our constructor is basically going to say, this is our target address of who we want to attack, so that's going to be here. We're going to put that into this variable. So we're going to initialize the contract. This is the address, and we're going to place it in this variable. So now we have our fallback here, and our fallback is partly key to this attack. We also need to utilize the attack function, but we'll talk about fallback first. So our fallback, actually let's talk about this next because it's kind of weird to talk about it now. So let's go to the bottom and do our helper. So our helper function is simpler. So we're just getting our balance to see if it's increased, decreased, or stayed the same. So it's a view return. We're going to return a uint, and we're basically going to get the balance of this address and return it back so we can see what that is. Our attack function is going to do a few things. So first, we're going to require that when this is called, that you're inputting something more than nothing. That's why it's basically saying, is the value greater than or equal to one way? I want to make sure that you're actually donating or sending money to the contract. Next is going to be a donate, and the value is going to be of 3-way, and it's going to be set to this gas amount, and we're going to send it from this address. And then last is going to be a withdrawal. So we're going to withdraw 1-way from our target. Now, once we've gone through this attack piece, we're going to call withdraw, right? And that withdrawal is going to then go off to the other contract. That contract's going to run through the withdrawal piece. And as it's running through the withdrawal piece, remember that our check happens, then our interact happens. And when our interact happens, that's going to then call back to our contract, and that's going to then hit our fallback here. So when it hits our fallback here, our fallback is going to go through a few steps. It's going to say, okay, if the balance of the target that just sent me this ether is greater than or equal to 0, then I want to withdraw some more. And then that when it calls that withdrawal one way again, it's going to then run right back into this contract. This contract's going to then check without ever going to effect. Remember, effect hasn't happened yet, so this is still empty here. And it's going to check, okay, does this account have more than 0 ether? It does, because nothing has been withdrawn in its world. It doesn't understand that it's going to be taken away because the effect hasn't occurred. So it's going to then interact again. And then this is where our loop occurs, right? So we're going to keep looping and looping and looping through. We're going to take all the funds from this contract before any effect occurs. And that's really how we're going to attack the target. So in reality, if I could get this to work, then it would be great. But as I said, I've tried and it hasn't worked. So just to prove to you that I'm incompetent, we'll run this together. So we have this set up. We have our reentrancy attack. We're going to deploy it to the contract that's vulnerable. So we could do just contract.address, and it'll give us this address here, which refers to this address here. So we will target, that address. We'll deploy it. All right, success. So it's deployed down here, so you can see we got some stuff. So our target is what we've set. Our balance is 0 currently, and we want to attack. So before we attack, remember we have a requirement of having more than 1. So if I try to attack now, it's gonna error out and say no, you can't do that. And that's because we need to send some kind of funds there. So we will say attack, and we will actually add some weight to that. So let's add 5. We'll confirm that. And then in kind of theory, this would work correctly, where we would hit the target, it would iterate through it, and then we would pull all the funds out, and we would have all the money. But when you do this, we can check our balance, and you can see that it's only two-way, so that's not the greatest. And if we get the balance of this contract, we can see that it's increased in way, and I've iterated through this probably like 20 times. That's why there's such a weird amount in here. Anyway, you can see this is slightly increased. If I would have shown you historically, you would have seen that it was probably 1.15 or not 1.15, but like this 17 would have been like a 15 or a 14. We put a few way in there, and we didn't get all the way out, sadly. We didn't take all the money. But like I said, we know a lot, we learned a lot, we just couldn't get it to work. So, internet, that's the challenge, and I will see you on the next level, which hopefully we'll achieve together, and that's called Elevator.